Something very interesting just dawned upon me. In maths, we have one of these limits that we have to evaluate. And this particular limit, not all the time, teachers will show how it is evaluated. And that limit is the limit as x tends to infinity of 1 plus 1 over x raised to the power of x. For any value of x, you could replace x with n, t. You could replace x with h over x. You could replace x with anything. As long as the limit is in this particular form, when we evaluate this limit, we are going to get e, the constant e, Euler's constant. So today, we're going to run through how do we get Euler's constant e. We're going to use a lot of concepts that we're supposed to know from our maths. We're going to use logs. We're going to use L'Hopital's rule. Now, L'Hopital's rule says if I have a limit to evaluate, I can just differentiate the numerator independently, differentiate the denominator independently, and then plug back my value into the function and evaluate it. That only works if the original substitution is indeterminate. So, what we're going to do? I'm going to do a couple of convenience steps here which are mathematically correct, and it's just out of convenience. First thing I'm going to do, I'm going to let y equals to the function. Next thing I'm going to do, I'm going to introduce logs on both sides because I want to get rid of the exponent. So I'm going to have ln y is equal to ln of the limit as x tends to infinity of 1 plus 1 over x raised to the power of x. Once you know your laws of limits, you know that once the function is continuous, I can slap the outside on the inside. So I'll slap the outside on the inside, and I'll have the limit, and I'll have the ln inside. Now I'm going to use a law, the law of logs, that allows me to bring the exponent down in front. So I'm going to have x in front of there. Hopefully you all know these laws of all your limits, or you know the laws of logs in order to calculate and understand these steps. Next, what I'm going to do is yet another convenient thing. I'm going to divide the numerator, which is what we have on the screen right now. I'm going to divide the numerator by x, and I'm going to divide the denominator by x. So let me include the denominator. My denominator here is 1. If I do this, this might make a little bit more sense. So what I'm doing, I'm dividing the numerator by x and the denominator by x. When I divide the numerator by x, this x will cancel with this x. When I divide the denominator by x, I'm just going to get 1 over x. So ln y is equal to the limit as x tends to infinity of ln 1 plus 1 on x divided by 1 on x. Now I'm going to use L'Hopital's rule. Now L'Hopital's rule says that if I differentiate, I must differentiate the top by itself, then I'll differentiate the denominator by itself. A lot of things that students do, they make the mistake when they see L'Hopital is a differentiation process. They say, well, you know, there's a quotient rule. It's not a quotient rule. Differentiate the top, big up yourself. Differentiate the denominator, big up yourself. Let's do a little recall how to differentiate natural logs. If I have ln of f of x, whatever f of x is, when I differentiate it, I'm going to get the differential of the function, and I'm putting it over the function itself. This is the function here, so let me differentiate 1 plus 1 on x. So 1 plus 1 on x is just x to the minus 1. I'll get minus x to the minus 2. So when I differentiate, the numerator is minus x to the minus 2 divided by the function itself, which is 1 plus 1 on x. That's the differential of the numerator, which is ln of 1 plus 1 on x. Take off this. Let's differentiate the denominator. The denominator is 1 on x. When I differentiate that, I'm going to put it divided like this. I could put it divided like this, but putting it divided like this could make it a little bit easier on our eyes, right? When I differentiate 1 on x, I'm going to get minus x to the minus 2. Changing this to multiplication, bam, 1 over minus x to the minus 2, wham, wham. And my function now is going to be the limit as x tends to infinity of 1 over 1 plus 1 over x. Now when I substitute infinity in the mix, infinity go in here, 1 over infinity is 0, and I'm going to get ln y is equal to 1. And using another law that carries me from logarithmic to exponential, I'll get e to the power of 1 is equal to y. In the beginning, y was the limit as x tends to infinity, and that's why this is equal to e. Hope you guys learned something.